Welcome to our deep dive into Database Models Explained, a guide to the top 6. In today's data-driven world, understanding how data is organized and managed is more crucial than ever. Database models are the fundamental structures that define how data is stored, organized, and manipulated within a database system. They dictate the relationships between data elements, the rules for data integrity, and how applications interact with the data. Choosing the right database model profoundly impacts a system's scalability, performance, and flexibility. Over the next few minutes, we'll explore why database models matter, outline their core components, and then delve into the 6 most prevalent types, both traditional and modern NoSQL approaches. This knowledge is essential for anyone looking to build robust, efficient, and future-proof data solutions. Let's begin with the most widely recognized model, the relational database model. Introduced by E.F. Codd in 1970, this model organizes data into one or more tables, also known as relations. Each table consists of rows, which represent individual records or tuples, and columns, which define the attributes or fields of the data. The power of the relational model lies in its ability to establish relationships between tables using primary and foreign keys. This structure ensures data integrity and consistency through ACID properties, atomicity, consistency, isolation, and durability. Structured Query Language, or SQL, is the standard language used to manage and manipulate data in relational databases, making it highly versatile for complex queries and transactional systems. Examples include MySQL, PostgreSQL, and Oracle. Moving on to an older but historically significant model, the hierarchical database model. Developed in the 1960s by IBM, this model structures data in a tree-like format, resembling an organization chart. Data is organized into segments or records, with relationships forming a strict parent-child structure. Each parent segment can have multiple child segments, but critically, each child segment can only have one parent. This one-to-many relationship defines the entire data hierarchy. While efficient for simple, well-defined data structures with clear nested relationships, querying data that falls outside the defined paths can be cumbersome and inefficient. It struggles with complex many-to-many relationships, making it less flexible than modern models. IBM's Information Management System, or IMS, is a classic example of a hierarchical database. Evolving from the hierarchical model, we have the network database model, standardized by the Conference on Data Systems Languages, or CODASIL, in the late 1960s. This model extends the hierarchical structure by allowing child records to have multiple parent records, moving beyond the strict one-to-many constraint. It represents data as a graph, where records are nodes and links define relationships. This many-to-many capability makes it more flexible and efficient for modeling complex relationships compared to its hierarchical predecessor. However, its complexity comes from the need to explicitly define navigation paths through the database, making queries often more intricate and application-dependent. The architecture can become very complex to manage as the schema grows, and changes to the schema can be quite challenging. While not as common today, it laid important groundwork for later database innovations. Next up is the object-oriented database model, which emerged in the 1980s primarily to handle complex data types often found in engineering, design, and scientific applications. This model applies concepts from object-oriented programming directly to database management. Data is stored as objects, which encapsulate both data and the methods or operations that can be performed on that data. Objects can have complex internal structures, support inheritance, where new objects can inherit properties from existing ones, and exhibit polymorphism, allowing objects of different classes to be treated as objects of a common class. This approach reduces the impedance mismatch between application code and the database, making it ideal for applications built with object-oriented languages. However, they faced challenges with standardization and performance compared to relational databases for typical business applications. Gemstone/S and Object Store are examples. Shifting gears to NoSQL databases, the first we'll discuss is the document database model. This model stores data in flexible, semi-structured formats, primarily JSON, JavaScript Object Notation, or BSON. Each document is a self-contained unit similar to an object and can contain varying fields and structures even within the same collection. This flexible schema approach means you don't need to predefine the table structure or columns, allowing for rapid development and easier evolution of data models. They are highly scalable horizontally and perform well for applications requiring quick retrieval of entire documents. Document databases are excellent for content management systems, user profiles, and catalog data where the structure isn't fixed or evolves frequently. Popular examples include MongoDB and Couchbase. The key-value database model is arguably the simplest of all database models, focusing purely on speed and scalability. It operates on a fundamental principle. Every piece of data is stored as a key-value pair. The key is a unique identifier, and the value can be anything: a string, a JSON object, a binary large object, or even a list. The database simply stores the value associated with the key and retrieves it quickly when the key is provided. There are no predefined schemas and no complex relationships or query languages like SQL. This simplicity makes key-value stores incredibly fast for read and write operations and highly scalable horizontally. They are perfect for caching, session management, and real-time data where simple, direct access is paramount. Redis, Memcached, and Amazon DynamoDB are prime examples. Finally, we come to the graph database model, a powerful solution for data with complex interconnections. Unlike traditional databases that link data by values, graph databases explicitly store relationships as first-class citizens. Data is represented as nodes, entities like people or places, and edges, relationships between nodes, like friends with or lives in. Both nodes and edges can have properties, attributes associated with them. This model is exceptionally good at traversing relationships quickly, making it ideal for social networks, recommendation engines, fraud detection, and knowledge graphs where understanding connections is paramount. While it excels at relationship-heavy queries, analytical operations across all data might be less efficient than in columnar or relational stores. Neo4j and Amazon Neptune are leading examples. With such a diverse array of database models, how do you choose the right one for your project? There's no one-size-fits-all answer. The decision framework involves evaluating several critical factors. First, consider your data structure. Is it highly structured and tabular, or highly flexible and nested? Second, think about scalability requirements. Do you need horizontal scaling for massive data volumes and users? Third, assess your consistency needs. Do you require strict ACID compliance, or can you tolerate eventual consistency? Fourth, consider your query patterns. Are you performing complex joins, simple key lookups, or deep relationship traversals? Finally, factor in developer familiarity and the ecosystem of tools and community support. Often, modern applications leverage a multi-model approach, combining different database types to optimize for specific workloads. In conclusion, we've explored the fundamental characteristics and use cases of the top 6 database models: relational, hierarchical, network, object-oriented, document, key-value, and graph. Each model offers distinct advantages and trade-offs, making them suitable for different application requirements. The landscape of data management is constantly evolving, with new models and hybrid approaches emerging to address the ever-growing demands for performance, scalability, and flexibility. The future points towards increased adoption of multi-model databases, which natively support various data models within a single database system, and serverless databases, simplifying operations even further. Understanding these foundational models empowers you to make informed architectural decisions and design highly efficient, resilient, and adaptable data solutions. Keep learning, keep adapting as the world of data continues its exciting evolution.